Now we're back live on YouTube. Cool. All right, then let's directly start with the second speaker, second talk of today. It's given by Peter Friz from TU Berlin and Weierstrass Institute of Berlin, and who will talk about rough stochastic differential equations. Please.
Okay, thank you very much, David, and all organizers. It's a pleasure to be here. So let me start straight away with telling you about my co-workers. There's Antoine, okay, still in Berlin, Coale until recently here now in Leeds, and some previous version of this presentation had more material that was joint work with Zorin Kranich, and I had to revise this a little bit, and so it's more about the first two people here, but I'll mention some joint work with Pavel as well that fits into this theme here. So what is the theme? It's rough stochastic differential equations, and there's a paper on the archive, and I've given, in recent time presentations on this, so I don't really want to drill into all definitions, etc., but convince you that these objects are here under your nose, whether you knew it or not. So to get started, let's talk about something we all agree. So let's look at the Ito differential equation. There's a drift term, there's a Brownian term here. Everything is multidimensional, and I will never spell out any indices. Now, I do insist that I like this generality of coefficients that can depend on the past in some progressive way. And as you will know, at least when there's no omega, but it's not hard to extend this, if you have Lipschitz coefficients B sigma, there's a unique strong solution, and etc., as this is what we teach our students. Now, if B sigma are not path dependent, they just depend on T and where you are, then we have Markov diffusions, time inhomogeneous to be more precisely, but that doesn't matter, and you will have your linear PDEs, the forward-backward story that you all know. If they depend on omega through some control process, if this is a progressive process here, and you let B sigma depend, then you are in the world of controlled Markov diffusions, and then you can look at optimization problems, optimal stochastic control. There's a value function, you get nonlinear PDEs, this famous HGB stuff. And in recent years, very popular, you have dynamics where you let the evolution depend on the law of the process itself. So this is the Mikin-Vlasov equation, or the Mikin-Vlasov theory that leads to nonlinear forward equations, non-local forward equations. So far, so familiar, at least in parts, I hope. Now, on the other side of the world, there is no probability, and there's only roughness and analysis. So people have written books on this, including myself. In a nutshell, I guess you wouldn't be here if you had no idea what this means. But in a nutshell, this is a deterministic path y, vector valued, that has a local expansion that should look familiar to you. This is like what you see in an Euler scheme, and here capital F here is what you pick up when you do some second order Euler scheme, also known as Milstein scheme. And this little bold X symbol, you should think of it as the iterated integrals of X. But if X is just a deterministic path of some bad regularity, then this doesn't make deterministically sense. In the Brownian motion setting, we'll come to that in a second. You can think of it, it's some iterated integral. But here you just put some good axioms on it that makes the algebra and the analysis, and that object is called a rough path, and I think it's very commonly known nowadays. So the important thing here is that if you put in this second order expansion and you are in some, let's call it level 2 regime, where the Hölder regularity is suitable for Brownian motion, if you want to think of X late in the day as a Brownian motion, then you have, this is a definition. Do you say that this remainder term here is negligible, meaning it's a little O of T minus S, and if you think of this expansion here, this guy here is order alpha, this should be 2 alpha, this would be 3 alpha typically. You can tweak the exponents and depending on F and etc. Okay, so there's a perfect theory for the stuff. If you have F, for instance, lip 1 over alpha, or C1 over alpha, alpha again is this here, so if you think of alpha a bit under half, that means you need a little bit more of C2. You have a unique solution, well posted with Terry Lyons, Sandy Davey. We'll talk about Cominelli in a second. Let me just draw your attention to the fact that if you know, in ether theory, putting in a T here is no big deal, right? Here it is a big deal because if you put in some bad T dependence, then you can easily mess up everything. So you have to be careful when you sneak in T's. Okay. The modern way to solve these equations is you solve them in spaces of controlled rough paths. These are paths that have a local structure that make them look like the driving signal. So X here is the driving signal together with this enhanced information. And so you're saying that Y looks like X with some modulation, so at the level of increments with some modulation function that may depend on S itself, but it's not crazy. So Y prime should be alpha held itself. And this here is an approximate identity. And so the error you make is this 2 alpha here. So this is of higher order than this bit here, which is order alpha. So this is the 101 of controlled rough paths. And in this, you can turn this, you know, you can guess how you take this guy here, you take this guy here. This gives you a semi-norm. So if you look at the smallest constant such that this estimate holds, this gives you Hölder type semi-norms. You can build Banach spaces and you can do your fixed point argument in these spaces. So relation to SDEs to the previous slide, I apologize to experts who are still bored on slide 3. The relation to the ether theory is if you randomize your X here, so this guy is deterministic, but you can take a random rough path. How do you take random rough path? You take a Brownian motion, so W is a Brownian motion. You take this mat bold W, these are the iterate integrals, everything's multidimensional. So these are random objects. Now, if you want, I can put in here omega, but okay, let's not do this. And so you can randomize this. And what happens when you plug it in, you have some omega-wise theory now that, you know, you can apply this omega-wise, and what you get out is a solution to your ether equation. So why is this a good idea? Well, there are books written why this is a good idea and many applications, and so this is not for today. What we want to do here is go back to ether. So we're back to ether equations, and I want to somehow separate the noise. Everything was multidimensional. So if I had a big, you know, Brownian motion, and I separate the first, I don't know, 17 components into the remaining 34 components, I call them B and W. This is still a Brownian motion, just a bigger one. So there's no point of hooking up a new theory for this equation here. But I want to treat these two noises differently. So B, I want to stay a Brownian motion in every good sense. W, I want to freeze. I want to think of it conditionally on this W. And so let me just fix notation here. I call this, so before I do any funny business, I call it a doubly stochastic differential equation, just to, you know, to remind ourselves that there's an SDE, but then I put in an extra patch of noise and the extra vector field. This is a second set of vector fields and Brownian components. So B and W are independent. If I think of this as a high dimensional standard Brownian motion, this would be independent. It will be independent. But I want to look at it conditionally on W. Okay, so first trivial remark. However, you want to formalize this. You know, if you freeze some realization of this Brownian motion here, then this is not a bounded variation path. And if you keep this one as a Brownian motion, it adds something that's not a finite variation, then you are outside the semi-martingale world. I mean, okay, so what? Now, this was studied for many years, and there's a concrete motivation that has to do with filtering, and I'll show you something next slide. So people have dealt with this for many years. Many people, this is almost a standard topic of stochastic analysis in the 80s and 90s, and it stretches to now. So how did people deal with this? If they wanted you can always do abstract nonsense and look at, conditional expectations or regular conditional distribution and stuff. But if you want to do some concrete, strong analysis on these objects, there was a way to do it via flow transformations. Goes back to, I've seen a paper by Bismuth 82, but I'm not sure who is the first one. In any case, if your F here has a reasonable simple structure, so no funny omegas around, and let's say for the sake of argument, it just depends on YT, then there's a simple trick. You solve this equation here. This is an auxiliary SDE that you solve at least for F nice enough, and let's do it in the Stochastic sense, then you can use somehow nice chain rule calculations, and then you play around. It just, I mean, Stochastic means here that the calculus is like if the same as if W were a smooth path, and then you just do a formal computation and realize, okay, what, you know, if I tried to look at this equation here, and now I think of this in a smooth Stochastic back of the envelope sense, can't I write y in different coordinates that are induced by the stochastic flow? And then somehow, you know, if I put in the argument, that would be the you know, the spatial argument you put into flow, and then transform away this thing here, okay? And so you get a new process. This defines a new process, y tilde, and that one turns out has simple Ito dynamics. So this is just a silly application of Ito's formula that tells you that y prime itself has somehow reasonable Ito dynamics, but the price it pays, you have to work in this somehow different moving effect. So it's an old idea. Let me move to this filtering example here. So it's still the question, you know, why would people do this? Why are doubly SDEs so important? So example number one is filtering. I'm not going into great detail here, but in a nutshell, the story is that you have a process here that has some noise B that is somehow, it also has some noise W, and the W has two purposes. It somehow affects the signal and it affects the observation. So Z here is the observation process, Y is the signal process. The aim of the game is to understand the signal given the observation. Okay, so as a concrete mathematical problem, you want to, here's some observable of your signal process Y, and you want to understand this conditional on the observation up to some time t. So there's a very concrete problem here, okay? And there's an old question, which is from an engineering perspective, very natural to say, well, if this is somehow, you know, this tells you something about the law of y t given the observation, how does it depend on the observation? So if I change my observation here, in the end of the day, the observation is something as an engineer you want to plug in, and out comes something. And it would be nice if that something depends continuously on the stuff that you put in. That means the observation. So there are some positive results, namely, if you have no correlation, and by this people in filtering mean that this term here is absent. This is somehow a special case, and that's good for many applications, but not for all. And if you have no correlation, then actually life is very nice, and it turns out this filter depends continuously on observation. So it's in the usual subnormal path space. Nice. If you have scalar observation, then this is still true. So we can't go into great detail here, but there's some special cases when it works. The general case, however, it does not work. This filter will not depend continuously on the path. And if you think of Ito SDEs, I mean, we all know, this is the reason why rough paths even exists, that the Ito map does not depend continuously on some driving noise. So why should it be true here? And it isn't. You can give counter examples, okay? That is until the rough paths entered the picture, and we'll come to that later. So of course, they don't contradict the counter examples here. They just tell you have to be a little bit more, you know, smarter how you look at the problem, but then you can say something more. And the other problem I want to raise here is the dynamics of the signal given the observation. And it doesn't matter if you look at Z or W. In the end, you know, this is filtering theory, do a Gessanov transform and make your Z a Brown. So it doesn't really matter. But we haven't really understood the dynamics of the conditional process. So the best you can do here, and I showed you on the last slide, is that you do some flow transformation. So you only have some indirect way of modeling the dynamics. And there's a downside of doing this. I'll come to that a bit later. So close related here is there are PDEs that are, if you think of this without the observation here, how the law evolves. There's the forward equation I mentioned earlier. Now you have the observation. Everything is distorted by the observation. So the SPDEs that model the conditional law. There's a Sakai equation. So again, I can't go into many details here, but this is many, let's say, famous probabilists have worked on this, and some still do. So to make the link back here from this SPDs to these doubly SDEs, these appear as stochastic characteristics of such stochastic PDEs. So yet another example where doubly SDEs arise. This is a story that goes back almost 25 years now. 98, coincidentally, the same year in which Terry Lyons published his first rough pass paper, or the rough pass paper, the original one. And so what they would have needed at that moment actually was rough pass. They didn't, it emerged later how these things come together. But so what they tried to do, or what they started, is the following. They again have a stochastic differential equation. And now they are interested in the setting where there's a control process here. You have to be a bit careful, you know. Okay, there's a control process here, and a control process should only be progressive relative to the information that's generated by this Brown motion here. And this one is, again, the one you try to phrase the best you can here. So, but of course, people didn't know how to phrase Brown motions in SDEs back then. Or not, maybe the other Lyons knew, not this Lyon. So what they did is they said, okay, well, let's look at some terminal payoff that they want to maximize, and then look at, so, you know, how you can store yourself to some terminal spot YT. This depends, of course, on the controls you choose. And then now you do everything conditionally on the information that's generated by this Brown motion. Okay, you can do that. That's a random variable here. So the best you can do here is take the essential supremum over all these controls here. So you can already think, if you think of the application, if you do some heuristic thing, there should be, if you have some optimal control that would do the best thing, it will depend one way or another on this noise here that you're freezing here. So that's a bit tedious, because it may depend on the whole noise from now till, you know, this is a dynamic object that you want to apply time little t, and it better be somehow progressive, so in particular adapted. And at the same time, if you freeze here the whole noise, then it also wants to depend on the whole thing somehow. So it's a bit fishy. And then if you put this back in, then you would have somehow here something that's not adapted anymore. It would be anticipating the information that's generated by W. So it's a tricky object, this one. Okay, even so, it led to a rich theory. This is this Leon-Souganidis stochastic viscosity theory, and of course they're PDE people, mostly at least. And so they, you know, this was some motivation that they didn't really explore in great depth. As a matter of fact, they had F constant here. And so the resulting PDE, that one, they you know, did a lot. I mean, they proposed somehow a pathwise theory. And again, that has to do with the fact that they dealt with F constant at that time. And so in that case, you can have a pathwise theory. But in general, as we all know, of course, you need some, you know, there's no pathwise Ito theory. So either you do rough path or Ito, something stochastic, but stochastic doesn't work here because this irregular PDEs. So they wanted to do a pathway theory. And I think the good way to do this is really a rough pathway theory. And there's a first paper on this in 2011 by Caruana, Oberhauser, and myself. We used rough flow transformations. And I should mention an important paper by Bukta and Ma. Here they are, Bukta and Ma, 2007, where they also looked at this problem. And there they used stochastic flow transformations. So the same technique that has been used in filtering. If you have this structure here, remember the F should be mostly harmless. It is here. You can transform this away. They also do you know, this in the Jokdonovich sense. So the calculus becomes a bit easier. It's not necessary, but you do. And this is the context of this one. And then they play around and get, you know, various informations about this random value function. So again, let me point out that there's no direct way of modeling this, unless F is constant, but even there, this has never been written. So there's no direct way of modeling this. The best you have is somehow some convolved understanding of this process via some flow transformation where the W somehow disappears, and then you can, you know, reverse this flow transformation to. So it's a bit, you know, it's not nice to work with. I mean, what does nice mean? Imagine you had some discrete version of this. You do some discrete approximation, some Euler scheme or something hands-on, and you want to show convergence. You want a local understanding of this process, of this equation. And if everything is given to you in terms of some some complicated flow transformation, then you can't really put your finger on the structure at the point, or it's tedious at least. So another one I like very much, financial mathematics. Many models like the stochastic Heston model or recent rough volatility has been a big success story in quantitative finance. They can be written in this form here, where let's say y is your, think of it as some asset price. We try to model it directly as a martingale. So think zero interest rates and we're interested in pricing. So we want to write down martingales. And there are two factors here, and somehow one is you should think of this as, well, okay. If you think here, you can put in some correlation rho, and here I put it down here. You can think that these two together in the right linear combination, they create another Brownian motion, but that one has a special role because that one drives I want to think of that as the one that drives the volatility process. Okay, so I've made this a bit more precise down here. So if you take for this one, really, you take here square root 1 minus rho squared times this whole chunk up, and here you take rho times, here for f you take rho times, and then again this whole chunk here. Then this does exactly what I said, that W drives the volatility, the stochastic volatility process. And then what you see up here is somehow a noise that drives the asset, and that noise, this is a linear combination, and this, with these coefficients here of B and W, you have a Brownian motion that's correlated with the one that drives the vol process. So this is a very generic setting in stochastic finance that covers many stochastic volatility models, including Heston and Steinstein and rough volatility and rough Bergomi and rough Heston and you name it. So let me put a few special cases here. If rho here happens to be 0, well, then something happens. Well, the F disappears, so this guy is just gone here. And then you have something that depends on your other Brownian motion. Then you can just condition on W. And what you see is that you have a time-dependent Brownian dynamics. So this is very convenient. You can just basically do option pricing by conditioning and then average. This is sometimes called the Hull-White formula. So if rho is not 0, then this dynamics, you can't really say what the dynamics are. It's a bit fishy. But what you can do, and what's very elegant, is to say that the law of this guy at some fixed time t, the conditional law, is actually normal. Okay, so we're not in the Black-Scholes world, we're rather in the Bachelier world and now randomize things. So we have a normal law here. And the mean, here it is, and the variance, here it is, depends. I should make this here also red, but maybe not now, here during the talk. So you can plainly see how the law depends on W as it should. Here is, and here is. Well, this is the mean of the variance. And this is very useful. Why is it useful? Because you can just do, you use the Tower property for conditional expectations. So if I want to do option pricing, I don't do it directly for YT. I do it for YT conditional first. This is Gaussian. That means I can use the Black-Scholes formula or the Bachelier formula if you prefer. And this is explicit. And then I do some additional averaging. So there's some implicit smoothing that's very useful for numerics, actually. So this is sometimes called the Romano-Tusi formula. It was in some 98 paper, I think, actually. So 98 was a great year. The thing here, it would be very difficult to get the dynamics right. How would you do the dynamics of this in the correlated case? I mean, here it was a neat answer, but here, unclear how to do the dynamics of this. There's no flow transformation you can do, by the way. Okay. Another one, Doubly SDEs and common noise models. So this is, I think, goes back to a paper by Michele Kogi and Franco Flandoli, and then in the rise of mean field games and mean field games with common noise. I mean, there are books written on this that have common noise in the title. Carmona de la Rue, to be more specific. So what is this? This is a ramification of McKean-Blasov. We mentioned this earlier. So here's the standard McKean-Blasov. Well, but now this extra bit is that everything is conditional on W. What is W? that's another noise component that you want to freeze. So the interpretation is that's the environmental noise, and if you use the language of diffusions in random environments, then this would be, conditioning on W means you're looking at the so-called quenched situation. So here everything should be conditional on W. So we really want to freeze W to the extent possible. And of course, this is, if you look at this is a bit not so easy. I mean, you can always do abstract nonsense, but to have a precise view on the resulting process for W frozen, that's not so obvious perhaps. So even so, Flandoli, Kogedi had conditional propagation of chaos results. Conditional dynamics, I don't think anyone could say much here. What is the dependence on W? So if you think of the filtering had the interpretation that W was somehow at least related to an observation, and you wanted to understand, does the outcome depend in a nice, quantifiably continuous fashion on the observation on W? And so here, from a modeling perspective, I think it's very natural to think of this as an environment, and I want to understand, how does the process I'm cooking up here, how does the environment affect this process? Sounds a very natural question, I believe. A very recent paper I came across by Laka, Stolnikov, Zhang, they also look at conditional Mikin-Vlasov problems and emphasize the need to have random coefficients here. So I emphasize this because if you try to hit this problem here with recent works of Beyeul, Delarue, where they have random rough driving noise, so then you could with some goodwill squeeze it in their situation, but not if you have omega dependence here. So for some detailed comparison, if anyone knows on these papers, we can discuss maybe later. So, right. I have made a long list of examples where doubly stochastic differential equations that you want to treat conditionally on W do appear. So I believe they appear left and right. As a rough pass person, what you want to do is replace this conditioning by some analytic deterministic procedure, which just replace this formally by a rough pass. Okay, so I'm just being formal here. This is what I would call a rough stochastic differential equation, provided I can make sense out of it. And of course, today's talk is exactly that. We can. And so what are the, why would that be interesting? So as a first result, if you have that these noises are independent, we always assume this. I mean, this is not the issue, right? Putting in correlations, this is what the model does for you. You have no interest whatsoever of making these guys here correlated. So these are independent. But so once you have such a theory in place, what it should do for you and what it does is that you can think of this, okay, so you create this or you find this y superscript x here, that's still a process, it's a solution process. I'll give you details, but it will be a process. And then you can randomize this parameter. So it's a family of processes, if you want, parameterized by this x. And if you randomize these x's, and you can imagine how you randomize it, namely you put the rough pass, let's say the Ito rough pass that you create by iterated Ito integration, you put it in because that is a rough pass. We saw it on slide 2. Then you actually get this defines a solution to y. And if you're well posted for this equation here, of course, then must be the same up to indistinguishability. So this provides you so it's, I mean, you did something. This is not just going in a circle here, because you have a very good view on the conditional process going this route. So specifically, you get a concrete view on the regular conditional distribution of y given W, and you see that this depends actually continuously on W as well, at least as a rough pass. So conditional as a function of this enhanced noise. So that appeared first in filtering. I'll say, okay, we talked about this very briefly already. So you remove the W here, replace it by some some rough paths, and then there's a little bit story if you do Stonovich here, and then it's a geometric rough path, blah, blah, blah. But so let's not get lost into these details. But again, big story here is that X is the observation. This is somehow the signal noise, or at least part of the signal noise, and you want to show robustness in X. So that's what we did in 2013 using this flow transformation. So I'll say it again. We did not give any intrinsic meaning to that equation, as much as I would like to say this, we did not. What we did is using a rough flow transformation. I've explained to you the principle that works just the same here as it works in Ito setting. So you solve this auxiliary equation now not as an Ito equation, but as a rough equation. And then at that moment, 2013, we had a good understanding of rough flows. And so you play around and you find that this transformed guy satisfies an Ito equation. Now you can use Ito theory on the transformed equation. And the whole rough path dependence is somehow now swallowed up in how these transformed Ito coefficients depend on X, and they depend there in a harmless way. So there's no more dx around, okay? So it's a nice way to do it, but what's the downside? No intrinsic local definition. If you try to do discrete approximations, for instance, good luck. This would not be very good for jumps, because if you had, you need these auxiliary flows, and this wouldn't work so well with jumps. Okay, let's not get into the jump business. Another downside is you have excessive regularity demands. So whenever you use flow transformations, it's not enough that this equation is well posed. You want the flow to be nice enough to play around with Ito. So this better be C2 or perhaps a little bit more for the rough case. So you lose. You have excessive regularity demands on the F here to make this fly. And last but not least, you have rigid structural assumptions. So if F here has some more general dependence, then the flow transformation quickly crumbles. There has been another way to deal with this problem. So this is DOR. This is Joscha Diehl, Harald Oberhauser, and Sebastian Riedl. I'm sorry I didn't spell them out here. So they say, well, I mean, how could you make, so what's the problem? Let's go back to the problem. The problem is to make sense out of this RSDE. So there's a B and there's an X here. Do you want to make sense together? So here is a way to do it. You just, instead of trying to push everything back to the Ito side, you push it all back to the rough side of the world, and you create a big rough path. I call it J because it's a joint lift of the Brownian motion and the rough path X. So remember, X is a rough path, so that comes already with second order information. The whole thing is called fat X. And so what you are missing somehow is the cross information between B and X. To make this an honest rough path, you need these cross integrals. So there are 4 bits. One of them, this guy here is part of your a priori information of X being a rough path. And then you have 3 with B that you're missing. But as you can see, B is a Brownian motion, X here is a deterministic path. There's no problem defining these by Ito. And the only one that you may not like is this one, but you just define it by integration of parts, and it's actually the natural limit in say, L2 sense. All right, so now you can take this joint rough path, stick it in here. So the B is the one that you meant for sigma. The F is the one that was driven by X, but because you take this joint perspective, you make this jointly somehow bigger set of vector fields. Okay, you can check that this is construction gives you something, a process here that is robust in X, but you pay a price. So now, because you push it all to the rough path side of the world, and the rough path theory wants somehow see, let's say, 2+ regulated vector fields. So now you have to do this too, and so you lose the good assumptions that you know from Ito theory, which is Lipschitz. And here too, this procedure has very rigid structural constraints. So if you try to do anything progressive that you would need for control applications that we have seen, that's a no-no here. And last not least, you make really an omega-wise construction here, so that the stochastic step is in checking that this is a good rough path, and then it's omega-wise sailing. And so you lost basically all the good things about Ito and martingales. It's somehow, you have to work hard to scrape it back when you need it. So here's the real thing. And it's basically that we have now a theory that does everything. Well, not everything, but everything that I talked about today, we can get in a very clean and direct way. And so again, this is the equation that I put down earlier as a formal equation. And now, I will show you in the next 2-3 slides that this is an honest equation that we have a very good understanding of. The trick is to come up with spaces of processes that somehow mix the stochastic and controlled features in some intricate way. And this was so we rely on some extensions of the stochastic steering lemma that was also mentioned in previous talks. So the stochastic steering lemma itself is not a terribly complicated statement, but it's just terribly smart and terribly useful. So I'll show you something. And I said it in words, so here's it on a slide. Basically, we can clean up this whole previous mess with these different ad hoc approaches and all their shortcomings. So you can now do the optimal Ito regularity for B sigma, the optimal one that you know from the rough path theory. And you can do progressive, non-smooth dependence. So we had these guiding examples that I showed you, and these are the ones that suggested which assumptions we should put forward, and this is exactly what happened. So here's a short one on stochastic steering, but I don't think that permits me from spending time on this. Let me just say this is in my second edition of the book with Martin. And you have it on his homepage. So you just Google, I don't know, Friz rough path or something, and you'll get the 2020 version, and then you should learn about stochastic steering. It's really great. Okay, so how do you really do it? So I need to spend a little bit more time on the assumptions here. So we have some progressive, or we can allow for some progressive dependence. B sigma are exactly what you can have and do have in the Ito theory. And for F, we have to be a bit more careful. I pointed out early on that you can't just put in a T dependence that will just wreck all the Hölder remainder estimates of the theory. So if you want dependence in T, and you sometimes need it, for instance, in this, McKean-Vlasov setting, then you need to put in some controlled structure in time. That means as a vector field, as a function of space, you also have to put in some extra structure when you move it in time. So it would be saying that when you move in time here, then to first order, it looks like an increment of the driving noise times something that's called f prime, which is also a function of y, plus some estimate, and then some remainder estimate. And that happens in a good space of vector fields. So that one I will skip. And to get you the idea of the whole story is, let's write this formally out. So this was the equation. I write it in integral form, of course. Now these two bits are harmless because I'm looking for some adapted process, and B is Brownian motion. So I know what this means. This is an Ito integral. The tricky bit one is this one. So let's try to expand it. And if you, so you freeze the left point as always, and then you do it, this is the expansion in rough path sense that you've seen before. So this is what you see in the Milstein scheme, DFF here, right? F is the vector for DFF. And then you may have something else that somehow encodes that your F may move in time. If you're happy with F time independent, you can forget about this term. And then you put in the second X here. So this is all fine. And there's something, this J here is whatever remains. It's a stochastic remainder because we're having a stochastic problem here. But it's, if you think, there are still some bits missing. I mean, we have B and X. If you think of this joint lift that I explained, if you did the regular rough path second order expansion, then this is just one of them. And there are three more cross integrals of B against X and X, B, etc., etc. So this one is not negligible. And remember, negligible was somehow 3 alpha here, which would be greater than 1, whereas here we only have 2 alpha, really, and alpha is, in this regime here. So this is not good yet in the sense that, if you think of this Davy definition we had earlier, we need something that's smaller. And so you have these hidden terms here. I mentioned one B against X. This is still lurking around if you look at some expansion here. And that is just not negligible, at least not analytically here. And so the idea is you can kill this term here, and the other ones are similar, but easy actually, but you can kill this term here by doing something smart. Namely, you take the conditional expectation relative to the filtration at time S, which is the left point of this guy here. And if you do this, then all such terms, and there are 3 of them that you would see appearing, they all drop out. And then what you have is negligible in this little old T-S sense. And so under the assumptions of the previous slide here, there is a unique RSD solution. Okay, meaning that you have one. So this, if you want, this is the essence of the definition, that this, you don't say that this remainder is small, but that this remainder is small after taking this conditional expectation. It's a little thing, but it resonates, of course, with the stochastic sewing. Stochastic sewing is called sewing, not sewing. So here it is, that it's all about, you know, having a random version of the classical sewing lemma where you drop in the right moment as conditional expectations to get some extra cancellations. So this is directly meant to exploit these ideas. So now we still need spaces where all this should take place. And I think I'm running out of time, but this at least I should cover. So we need spaces. Classically, we used controlled rough path spaces. So these were spaces of pairs y and y prime, where we could make the fixed point argument get going. And here we have, well, stochastic controlled path, and there, you know, classically for the controlled rough path, you would say, okay, let's look at the increment of y, and then there's some increment of x, and they look alike with some modulation function, which here is just f of y, because the structure of the equation tells us this. But this here, you don't have a chance that this guy here alone is of controlled in the sense that the remainder is of order 2 alpha. This won't happen. Why not? Because you have this extra Brownian bit around, and this hammer, you know, still has regularity 1/2 minus. So you're not there yet. Okay. But if you could get rid of this term here, then you're good. Then you're good to go. And so it's the same principle as before. What we should do is not try to look at the remainder, but look at this conditional remainder here. And after putting in this conditional expectation here that kills that term, then you're down to 2 alpha, and that's somehow, this is the origin of the technical definition of a stochastic controlled rough path that you can look up and enjoy in the archive version. So whenever I write something like this, I mean it in moment norms. Okay, what else? Now, there's a technical problem that these stochastic controlled rough paths, they're great, but they're not invariant under composition with, let's say, regular functions. And so here you have y, and here you have f, or an equation here. Where's the equation? Here you have y, and here you have f of y. So this is a real trouble, because every time you apply f, as long as it's nonlinear, then you lose integrability, and you end up in a worse and worse space. And so how can you ever close the loop? And there was it took us quite some time to understand how to get out of this hole. And so we had to work to find scales of 2 integrability parameter spaces. And it turns out that when we compose them, only one of them has a loss. And that's the one that you can actually take to infinity. So we're talking about L integrability. So what you don't want is to solve the whole equation in L infinity, because then not even Brownian motions in there. But if you split it up in that way, you can take the n infinity, and of course, infinity half is still infinity. So if you have a loss, like think of multiplying 2 L2 functions, unfortunately not L2 anymore in general, but if you multiply 2 L infinity functions, they are. So we can take n infinity and close the loop. I don't have time for this connection to rough semi-martingales, so I'm very sorry, Pavel. Very nice paper. Up. And so just to give you something to look at, which is a bit more precise. So here's the definition, this is the solution. And it's either to say that this pair of y and fy here, so y and fy, somehow this is the natural controlled object here, is a stochastic controlled rough path, and the equation holds in a well-defined integral sense, or equivalently, we have this David type expansion that I showed you earlier, where you have to make damn sure that you take the expectation here, the conditional expectation at the right moment. Okay, here's a theorem, strong existence. uniqueness, stability. You can be fully quantitative on all this. So, whatever you want to tweak or push or notch, this is it. Here it is. So I realize I'm getting quicker and quicker now. Applications, well, I guess you will trust me that, or you will hopefully agree from what you have seen, that you can go back now to these initial examples and just revise everything. And they all were complicated and suboptimal because they used complicated and suboptimal tools. In particular, this flow transformation method, but also this random joint rough mass lift technique. So you can go back and do many, many good things here. So for instance, if you do this pathwise control business, now already the formulation of the problem is much easier because you don't have to worry about, this possibly two filtrations and, all this essential super business. This all disappears much easier here. And you can, in the end of the day, still randomize, go back. So you say very precisely things about the original problem. One benefit of this is that you can easily, from the stability estimates I showed you, get very precise information on the value function of such a problem here, which actually relates to an open question that was given in Bookdan March 2007, and also relates to some recent work of Gerda Laguet and Ben Seeger. So here's an estimate that you can get up. Dynamic programming, imagine the pain you have to suffer when you don't have a soup here, but an essential soup, and you have to worry about all the measurability things. So all this disappears here in the rough setting. And if you want to give a lazy proof, if you're a lazy person, then you just use here stability of, in rough pass metrics. So you can just work with a geometric rough pass. That's the limit of smooth pass. Dynamic programming holds when X is deterministic and smooth, because that's a special case of a classical situation. You pass to the limit here, no problem. And there it is. You can also give a direct proof, but then you have to reopen the whole box of how to prove dynamic programming for controlled Markov diffusions. If you want to get some rough path stability and some nonlinear PDEs, this was, the message of this paper I mentioned earlier, you can do that again here, but now with very relaxed conditions. And again, you have other benefits if you think of discrete approximations to such nonlinear PDEs. Up, rough McKean-Vlasov. This was just to show you that there's a well-postness theory for such equation here. So the difference is I don't have a Brown in motion W that I want to do conditionally. So I just freeze it as a rough pass from the very beginning. And now I have a rough SDE in front of me, and I can do everything I want to do directly here. And then in the end of the day, I can randomize and go back to the previous thing. But I may also want to put in, I don't know, some fractional Brown motion or have fun with something else. So it's a very decisive quenched version of these McKean-Vlasov, conditional McKean-Vlasov equations with common noise. So here, I don't think we want to go into great detail here. Propagation of chaos also works. All right, proof, I think we skipped this. And I am 4 minutes over time, I believe. So this is the right moment for Outlook and references. So we can do, there's a forthcoming paper with, there's several forthcoming papers, so because there's so much to do, but we can certainly do rates here. So we can do strong approximations that somehow unify a bit what's known for SDEs and RDEs. Then a fun one is you can do backward stochastic differential equations, or more precisely, doubly backward stochastic differential equations. That's something, famous paper by Perdue Bang from the 90s. And you can somehow robustify the second Brown in motion in there. You go to a theory of rough BSDEs. There was already a previous paper with Yosha Deal on this using flow transformations. And now you can somehow, you have a good enough knowledge about all these spaces to do this directly and intrinsically and really understand what's going on. You could do partial Malevin calculus, heat kernel expansions. So people have done this in the past for, especially, in view of this filtering problems. There are many papers in this, so they can all be revised. I'm not sure, everything has to be written that can't be written, but we'll see. Financial modeling, I like this very much. That what I showed you earlier, which actually just occurred to me this afternoon. Then we talked about nonlinear PDEs. So if you have this McKean-Vlasov things that I showed you, if you superimpose some Markovian structure, so we didn't really have a Markovian structure, but we can have one. And if you do, then of course there are PDEs or rough PDEs to be more precise. If you leave your X as a rough path, and then you have a theory of nonlinear, non-local Fokker-Planck equations with rough common noise. Voila. Controlled McKean-Vlasov. Okay, we saw this. There's a clear outlook to combine this control business with McKean-Vlasov. So this, we are now approaching the world of mean field games, and that's a busy world with many good people working in it. A natural question is to what extent this somehow rough path story here extends to singular SPDs a la Martin and Gubinelli and Kelepakovsky. So we'll see at least a version of this stochastic sewing lemma, which is fundamental to the regularity structure setting, has been proven by a student of mine in Berlin, Hannes Kern, and the stochastic reconstruction is on the archive. And so here are a few papers, and there are a few more coming, and thank you all very much.
Thank you very much. Are there questions?
Sorry, can't you show once more the slide about rough semi-martingales? What is the definition of rough semi-martingales? There was on one slide.
Yes, very good. Here it is. So there's a structural theorem that I didn't show you on stochastic controlled rough paths that says they have a sort of a decomposition into a martingale and a sort of random controlled rough path. It's actually in a Banach setting of moment spaces. But anyway, so in essence, it's a combination of a martingale plus a random controlled rough path. So you can come from the other end of the world and say, okay, why don't we formalize this straight away? So let me say we take a controlled rough path. So we know what this means. There's somewhere in the background, there's a fixed rough path. It's not written here in the slide, but you know, X is a fixed rough path. And so Y prime, they are controlled. They are controlled by this fixed path in the background. Let me write X controlled, because X is that fixed path that should be written somewhere. But otherwise, I want them to be adapted processes. So Y prime, as processes in T, they should be adapted. But they also should be omega-wise X controlled with all the usual Hölder conditions. And in fact, here, if you talk about semi-martingales, Hölder is a bit inappropriate. So you should, at one point, we should move to P variation. So let's do everything P variation. It's a bit, you know, more cumbersome sometimes to write down, but it's not very different. And so then you make this definition here that you say a pair of processes such that the first level, if you want, is the sum of a local martingale plus a controlled path together with this, you know, modulation function of this path Y that makes the pair omega-wise controlled rough path. This pair here, you call it the rough semi-martingale. Okay. You can define what you want, who cares? The good thing about these rough semi-martingales is that you can come up with a reasonably, or actually quite satisfactory theory. So you can integrate against rough semi-martingales. You can compose rough semi-martingales with regular functions and outcome again rough semi-martingales. So you can do many things, even in a Cadillac setting. So it's a powerful theory, and you can be very quantitative about them, but you have to leave the world of Hölder regularity. And so if you think of somehow P variation and martingales, the one thing that should jump in your mind is Lepingle 76, who proved a very elegant inequality that tells you that the classical PDG inequality that you all know can be sharpened at no price by switching from the uniform norm, so the infinity norm that you usually put in there, to the P variation norm with P anything greater than 2. So this is the classical Lepingle. And now if you think about this here, you to get all these estimates right, you need several sharpenings of this Lebesgue inequality, and they are interesting in their own right. And so that allows me now to show you even this slide here. So this is an improvement of the Lebesgue PDG inequality that appeared in this analysis of probability paper this year, or at least it's forthcoming. I'm not sure where it's exactly, with Pavel Zorin-Kranich, who I should really emphasize here. And as you can see here, the simplest case would be that you take here, so these are, M is a local martingale. So what you have here are stochastic integrals, but you think of them in this 2-parameter rough pathway. So when I write the delta here, I really mean here it's the delta of, let's say, R minus delta S, and then dmr, and from S to T, and this P variation here is in this 2-parameter sense that is relevant in rough path. And it's exactly in this rough path P variation sense that you measure things here. And if you look at these exponents here, this is exactly the right scaling that, so the Y, you don't know anything more than it's being let's say a Cadillac process. Here's the Y minus to make good sense. And then you estimate this here with some sample pass P variation sense, you know nothing else, but M is a martingale. And so here you can do, you can measure it in the bracket sense, or with the square root function. And then you have the moment norms, which are the ones that you expect from Hölder. So everything is optimal. And it's these type of estimates that allow you to make this rough semi-martingale theory very quantitative. The only thing that the rough semi-martingale theory has not delivered, so why is this paper with Pavel not the end of all things? It could not capture the feature that you need to have well-posedness of rough SDEs. And specifically this iteration that I mentioned, when you compose, that you lose integrability. There's no way to do this unless you have two integrability parameters, and I don't know how to work them into this setting here, but in the setting that I presented today, it works very nicely. So it's very compatible with the stochastic Soring lemma that we saw. And this is not clear how, I mean, in a sense, it's the intersection of these methods here with stochastic Soring that I think there's still a deeper understanding coming, but I'm not sure when and by whom or by who.
Sorry, can't you explain what is delta Y minus? What is delta?
Okay, so let me put it this way here, and then I can write it here as YT minus, so Y R minus Y, as the delta is only the increment here. And then I have this is what I mean. There's a minus here. Measure. And so here this P variation norm is really the 2-parameter P variation norm that you have in rough paths. So strictly speaking, I should, now it becomes a bit ugly, but it's, now you know what I mean.
Thank you.
Thank you.
Thank you.
Maybe there's also a question in the chat, which I mean, Peter has maybe seen. So the question which came up 50 minutes ago was, can this, so the double SDE extended to double SPDs? I mean, I think you comment on it a bit, but maybe.
So the short answer is, I see no reason. Okay, the problem is SDEs is, there's a great agreement in the community what we mean by SDEs, at least if you talk about strong SDE solutions, and then, but SPDEs, there's so many different versions, and there's a spray of different, ways to look at them, and different people like different things. So it will depend on what whoever asked the question wants, but I can surely think if you take, let's say, a stochastic heat equation with space-time white noise, the way that was studied, for instance, I mean, this is the part of subject stuff, but it was recently viewed from a regulated structure perspective by a paper, nice paper by Martin Heira and Etienne Pardou several years ago. So I think in that setting you could, I see no reason why you. So it's a good question. I think it's a good project ahead for, again, different people will want to do different things. There will be cheaper ways of doing it using this this joint rough pass lift technique I presented. In case you remember, we had this. Where is it? So where is it? Here, this one. So if you have your Brown in motion and you have the noise that you conditioned on, so you want to treat it analytically, then you can do some joint rough pass, and so you can translate this idea quite easily in this setting of regularity structures. So you have, let's say, one sort of noise that you want to keep as a noise, another batch of noise that you want to treat like a model in the language of Martin. And then you think of a joint model, which is now random, that mixes them together in the way that you want. And then you can solve it omega-wide as a analytic singular SPD driven by models, a la Martin. And then you have to think about the renormalization theory, but this will work. This wouldn't be quite the point of this work here, because the point of this work here was not to do this. I mean, this would work. This would give you something for some SPDs, but it's a better way to combine it on a more fundamental level. And so for that, the stochastic reconstruction that I mentioned at the end will come in and will play a role, or some version of it will play a role. But we're quite busy actually cleaning up everything we want to clean up in the SDE setting. So time is finite, but it's a good direction to go for sure.
Maybe for the sake of time, let's thank Peter again, and well, thank you very much. Very nice talk.
Thank you all.